And here we are. We're back. Sorry about missing class one day. Something came up and I couldn't make it. So I think we all enjoy a day off every now and then. I'd like to think so. 17 people. Let's wait a couple minutes. See if anybody else shows up. Ison's here. Got our respondent from Azerbaijan. Thank you for coming, Ison. Christopher James is here, and you know what? I can't see his face, but I know he's not smiling. I know it. Farouk, my man. Farouk's one of the more intelligent students I've met. I haven't met you, though. Jason Bonilla. Michelle Simmons. Bring your faces up. Come on. I feel like I'm sitting in a room all by myself. Santange. Bonilla. Bonilla. Hey, is that a man bun or is that just fluffy?
This is crazy right now. That's why I had the camera off, to be honest.
You don't mind my saying it looks extremely cool. If I had hair on top of my head, I would shave the sides. I would, but
they're usually shaved, but right now it's all over the place. I need to get it fixed up soon. It's been a while.
Well, the finals are over. You got better things to do. Rocky and Vanessa, my two people have been with me since Bio 101. Tyler the Creator. Who's Tyler the Creator? I don't know. Vanessa says hello. Oh, Tyler. There you are, Tyler. Kwame is here. Yusuf is here. All right, why don't we do this? Let's have our quiz first so you people can get in right now and have your quiz. I'm going to go to Moodle right now and activate it. And when I do, you'll have 5 minutes to finish it. It's pretty short and it's only 2 questions and you've seen one of them before. So, show quiz, boom, it's up. So go ahead and do that. And we'll meet back here in 5 minutes. We meet back here. We didn't go anywhere. Just metaphorically meet back here. If you just showed up, there's a quiz in Moodle. You got about 3 or 4 more minutes to do. Here you go, sir. Hey, buddy. Okay, what time did I start that quiz? Is this quiz over yet? Tell you what, bring your face up when you're done with the quiz, just so I know. Dun, dun, dun. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Vamos. Vamos a continuar. Let's continue our lesson today. Hide it. All right, so, oops. Let me share my screen and we will get started. So I was going to talk about, do a little more from chapter 8 and talk about differentiation of blood cells. And I read over the chapter and I found it tedious. So I decided not to do it. So instead, we're skipping ahead to chapter 10. And I think this fits better with what we've done before because we went through murulation in chapter 5 and we kind of set up the main body axis. And I said, here's your somites and they become limbs. But, we stopped there. So now we're going to see how those cells that were, going to be limbs go out and be limbs and stuff. So we're going to make limbs today. We're going to make chicken wings today, and we're going to have them fried in buffalo sauce after we're done. Just kidding. Just kidding. Okay, so this is what we're up to. So this is a little bit of review from chapter 5. If you remember, we had a dermomyotome on top and a sclerotome on bottom, and that dermomyotome then split up into 2 myotome layers and 1 dermatome layer. And the dermatome became the dermis of the skin, so that's going to line the whole underneath of the epidermis. And then you had the myotome that's proximal become axial and back muscles, and the more distal then is going to become abdominal and limb muscles. And what it becomes depends on where it is in the AP axis, which is determined by its Hox genes. So we're going to be talking about Hox genes again today. Let's see. Okay, yeah, so well, let's just continue on. There's also, don't forget, this other lateral mesoderm here. If you remember, somatopleural mesoderm, and then there was a coelom, a space, and then splenopleural, I can never pronounce that word, below it. So that somatopleural mesoderm is going to come into play here as well. So Hox genes, we all remember our Hox genes. So they start expressing from the ones, right? All the paralogous 1 genes are expressed first, and the 2s and the 3s and the 4s and the 5s and the 6s. And then even at these early stages when there's no differentiation yet, right? These cells are just going through that pre-Semitic mesoderm stage. Those Hox genes are already being expressed, and the tissue is determined, right? Specified or determined. It's going to be what it is based on those Hox genes. And this is the experiment that showed us that you take this chunk of early mesoderm from that pre-Semitic mesoderm section. You take it from somewhere low down on a later neurula. You put it up higher on the neurula. It still develops, but it develops from the position it was in when you took it out. So this should be like this. It's like should be this somite was put up to here, so it becomes like that. So that's going to be really important to tell us where to put some arms and where to put legs, right? Arms always end up here, and then you've got a space, and then you've got legs below that, and then you've got your tail. So Hox genes are going to tell us which segments of the human or the chick body to turn into each of those things. Okay, so that's just a little review from chapter 5, which I know you didn't need because you've been studying these notes all along. Okay, the vertebrate limb. So all limbs, of course, are based on that first intrepid amphibian that crawled out of the water and ate the insects that were abundant because they had no predators. I'm just making this shit up. But it's all based on a humerus as the large bone, most proximal, 2 bones next, more distal to that, all in radius. Then you've got carpals, and then you've got 5 digits. So this is the basic plan, and everything's based on that. Here with the human, our number 1 digit's a little different. It's rotated around so we can touch our other fingers. Here with the cat, we've got nails that retract. That's all I know about cats. Here with the bat, you've got the number 5 digit that's really long, and that helps to hold the thin membrane that is the wing of the bat. And here's our bird, which has only got 3 digits. So that's kind of an interesting thing to talk about too, because this is all like Evo Devo, which I hope to get to eventually. Like, you start with this basic plan, and then through development, it changes from that basic plan, and that gives different traits, which can then be selected. So you end up getting evolution based on slight changes in these developmental patterns. And already just how complicated development is with different transcription factors and different growth factors and things coming up and down at different times and at different levels. You can imagine if you had a slight mutation in one gene, it could cause a big change in the development of that limb. And if it made a positive influence, it would be kept in the genome, in the gene pool. Okay, but here's again our bird. And another thing is, like, as different organisms lose digits, as they evolve to have fewer digits, they always lose them from the outside in. So you can see your bird has got 3 digits, so it lost the outer 2 and it's left with the middle 2. If you look at a horse has only got 1 digit. So when a horse is running towards you, he's doing this. Yeah, our friends, the horses. So it always changes from the outside in. Okay, so which slide am I on? 5, okay. So we're going to talk mainly about the chick. And again, just like I said before, when we're talking about neurulation, it's just easier to work with a chick than anything else. Maybe not for the really early embryo stuff, because all that early stuff happens while the egg is still being formed coming down the oviduct. But once the egg is laid, you can follow everything really easily, because you can just cut a little hole in the shell and then get down in there, do whatever you want to do, cover up that hole and let the egg develop, and then see what happens. So chick is really, at this stage, chick is the easiest thing to do. The mouse is inside the womb of the mother. So usually mouse stuff is kind of like, do your change, let it through genetic means, not manipulating, but just, knock genes out, and then let them develop to a certain point, kill the mother, take out the fetus, see what's different without that gene happening. So chick is much easier. And when you're done, you get chicken dinner, right? You let them develop. I'm kidding. Okay, so what happens is these limb buds are going to form from that lateral mesoderm, which includes the somites and the somatopleural mesoderm. And one thing that's kind of really important is this apical ridge. So this is ectoderm or epidermis, and it's going to form on the outside edge of each limb bud. So this is the wing bud, and this is the leg bud here. And that apical ridge, it's basically thickened ectoderm. So most of the embryo at this point is covered by a single layer of ectoderm, and this is a thicker layer of it. And what we'll see if we look inside this, I'm going to skip ahead a little bit, is you've got inside the limb bud, you've got mesodermal mesenchymal cells. So they're still kind of motile, they're moving around, they're not all that well organized. And at the tip, you've got cells that are proliferating pretty quickly. So they're dividing a lot out here, and that's causing extension of the limb bud. Behind this wave of proliferation, these cells back here are still dividing, but not as much, and they're starting to differentiate. So they will come together to form the bones. So I'll talk more about that later. And here's your apical ridge from a different angle. So it's coming across the outer, the most distal edge of it, and it's between the dorsal and ventral sides of that wing, which again, I'll talk about in a second. Okay, so bone structure. So here we are. This is I don't even know if this is an X-ray. This might even be a light microscopic view of the early wing. So this is all cartilage now. This will eventually, it always starts out as cartilage and then ossifies into bone. So here you can see at this stage, you've got your humerus, radius and ulna, yes, radius and ulna, and then your 3 digits sticking out. And across the bottom side, you can see these, I think they're called feather buds. So you know, there's a lot of big feathers coming off the bottom of the wing there. And so they're already starting to develop here, not the feathers themselves, but the structures that will form the feathers. So in terms of, I don't know what we call this, geography. If you like, we'll be talking about anterior versus posterior and dorsal ventral. If you ever get lost, this is what you do. Stand up and put your arm out like this, right, with your palm facing forward. And if you do that, the front of your arm is facing forward. That's all ventral. The back of your arm is dorsal. Anterior is your thumb side. Posterior is your little finger side. So that's the way we're going to be talking about here. Anterior over here, posterior back here. Dorsal is on top here, and ventral's underneath. And then the other thing that's really important is proximal versus distal. Proximal is closest to the body axis, and distal is farthest away. So we'll be using those terms a lot here as we go through this discussion. As I said before, we've got two different tissues in this early limb bud. You've got your ectoderm on the outside, which is epidermis. I shouldn't say ectoderm, it's epidermis, which is of ectodermal origin. And then we've got the inner core, which is mesenchymal tissue. Now, this mesenchymal tissue is made up of two different types, coming from two different origins. The stuff that's going to condense into cartilage and then become bone is from that lateral mesoderm, the somatopleural mesoderm. And then, so you can imagine, let's go back real quick so you don't have to imagine. Oops. Okay, so that is like out in here. So as the limb bud starts to form, that somatopleural goes out, and then this myotome here grows into it. So you've got one type of ectoderm, and that's the epidermis all around. And then you've got two types of mesenderm, some from the lateral mesoderm that becomes cartilage and bone, and some that comes from the somites, which will be muscle and also blood vessels. So remember, the blood and blood vessels are also on mesodermal tissue. They come from the somites as well. Okay, so again, your apical ridge, keep an eye on that. And here's a view looking like into the wing, like that. So the apical ridge, you can see it's standing out a lot on the outside. And then here's the dorsal side of that wing and the ventral side of that wing. And this development starts right against the body. We'll talk about this more, but starts at the body and it pushes that limb bud out. And as the limb bud is going out, behind it, differentiation is happening, and that limb is forming as the limb bud goes out. And then afterward, after the limb is out, nerves will invade, and that's your neural crest cells crawling out there to form the somatic nervous system. Okay. Next, Hox genes. Got some Hox genes going here. What do you mean, Hox? Okay, so here is our anterior and posterior of the body axis of the main axis here. Here's your 3' Hoxes, and here's your 5' Hoxes. And so in this area here, you've got expression of HOX4 and 5. So HOX4 and 5 will cause the production of TBX5, and that's going to make a limb. And TBX5 is doing that because it's causing the expression of FGF, and then you get this positive feedback situation here that we'll talk about in a second. But TBX5 is the key here. HOX4 and 5 cause that to come up, and that makes this a limb, basically, hinting that there's something more coming. So down here, we've got HOXs 8, 9, and 10, and that causes TBX4 to come up. Okay, so TBX4 then causes PITX1 to come up, and then PITX1, reinforces TBX4. So you always have this mutual admiration society going on between transcription factors. TBX4 comes up, and that causes PITX1 to come up. And that then specifies this as a hind leg, okay? So this is TBX5 is going to be the wing, and then TBX4 is going to be the hind leg because PITX comes up. I believe they talked about some experiments where they knocked out TBX5 and they still got a normal limb. Oh, I forget. I'm not going to talk about it because I've forgotten exactly. I kind of skip over a lot of the experimental stuff because I'm always more interested in what happens than how they figured out what happens. Okay, but remember, PITX specifies hind limb, and we'll talk about that a little more later. Okay, so here's what this is what I came to tell you. Okay, so in terms of the anterior posterior axis in the whole organism, that's Hox genes, and that tells this is going to be a limb bud. Now, when this extends out as a limb bud, now you've got another anterior posterior designation, and that patterning is going to be because of local factors being released. Okay, so the Hox genes just say there's going to be a limb here. The patterning of the limb is caused by local factors, FGF and sonic hedgehog, which we'll see in a second. So, and this shows you an experiment that kind of exemplifies that. So you take an early embryo with a leg bud and a wing bud, and they take a chunk of tissue out here that's proximal, so it's really close to the axis. This, if you did cell lineage tracing, would become the thigh of the leg. So we're taking out this chunk that should be thigh, and we're putting it at the apical edge or the most distal edge of the wing bud. And what happens is it's still going to be a hind limb, but now it's apical. It's the distal form of the hind limb. Okay, if that makes sense. So what I'm trying to say here is because it had these Hox genes expressed, it's still going to be a hind limb, but because it was on the outside of the limb and not on the inside of the limb, it became a foot rather than a thigh. This would have been thigh, but it became foot. Does that make sense? I'm hoping that makes sense. I'm not getting any feedback here. But basically the point I'm trying to make is that you've got two different factors involved in patterning this limb. The Hox genes are going to determine where in the whole overall body axis this is going to form, or what it's going to be in the body axis. So you don't get, a wing coming out of the hip sometimes. And then patterning from the limb bud out is all based on local things being released. And here's another hint as to what's causing these local factors to be released, or local. Here's one of the local factors that's going to be important here. So the Hox genes, so if this is the limb, or the upper limb, the wing, at this end, the anterior end of that limb bud, you've got HOX4 being expressed. And as you come down to the more posterior, now you've got HOX5. And that Hox gene is then, and also HOX9, which makes no sense to me, so let's not talk about it. So HOX5 down here causes this area to become the zone of polarizing activity, okay, ZPA. So you can imagine at this point, this is going to be another one of those point sources of a hormone, and you're going to get a gradient of hormone concentration. So that's why this is a polarizing zone, a zone of polarizing activity. And the hormone that is going to be releasing is sonic hedgehog, another one of our favorite hormones. Okay. Okay, so that's part of the, see, I find this chapter kind of frustrating. I spent all day today reading it because it kind of comes in bits and pieces and then it doesn't, I want a story from top to bottom and it doesn't give me that. I'm finding it a little bit frustrating. That's what I'm hoping to give you, the story from top to bottom. Okay, so the next thing to talk about is this, which is how does that limb extend out? What makes it go out? And that has to do a lot with FGF. Let me just back up my notes a little bit. Okay, so I didn't tell you this. Oops, oh shit. I haven't told you this before, but when I say FGF, I'm just being general because there are a lot of different isoforms of FGF, and they're all controlled from different upstream regulatory regions. So you get different expression of different FGFs at different times. Their effect is always the same, though. You're always getting the same result because it's still FGF, and I think it's the same receptors everywhere. But you've got isoforms of the hormone itself that come out in different places at different times. I never get into that because it's rare that it's all that life and death. I'm going to talk about it a little bit here because it is a little different. So TBX5 then, we're looking again at the wing formation. TBX5 is going to cause the production of FGF. FGF is then going to interact with that apical ectoderm and is going to cause that apical ectoderm to release FGF8. So FGF8 then, is released and is coming inside. There's nothing outside. So it's released inside and it stimulates these cells to release FGF10, which then releases FGF8, which releases FGF10. So this is another one of those mutual admiration societies where the hormone is sustaining itself more or less. And remember, FGF is a tyrosine kinase receptor, RAS, MAP kinase, cell proliferation kind of a hormone, right? We talked about that last time, how it causes cell division by activating cyclin D and the CDKs and all of that. So you've got cells out here that are bathed in a high concentration of FGF. They're going to proliferate, right? They're going to divide. As they divide, they're going to force that limb out. So, okay, this is a different experiment. So that extension of the limb is going to be caused by growth at the tip of it, which is being supported by FGF, this FGF positive feedback pathway between the apical edge and the mesodermal cells on the end. So again, now we're going to stop and look at an experiment because this is where the chapter jumps back for some stupid reason. So anyway, how do you know this apical ridge is really important for this and really causing this to happen? Well, the experiment they did back in the day was take an early limb bud here at 3 days, take the apical ridge off, and you only get a humerus. It stops extending after that. If you half a day later take it out, now it goes as far as there, a little bit further, take it out, goes as far as there. If you let it go the whole way, that's the whole limb. So the idea is at the time you take that apical ridge off, you stop getting extension and it just differentiates behind because you don't have FGF anymore. So it's going to go into that differentiation pathway. So that's how you can tell that this apical ridge is important for this. And how you know it's FGF being released from the apical ridge. Here's an experiment they did where they took the apical ridge off at this, day 3 early embryo stage, and they inserted some beads that release FGF. Remember why we use beads? It's because you can soak these beads in a hormone and there'll be a point source and release it over time. And that's going to mimic um, what they think is happening with this apical ridge. So you put that FGF there, and you get almost a normal arm out of it, okay, or normal wing. Not quite right, because obviously just having a bead and putting it somewhere is not going to be the same as having that natural apical ridge there. But, you know, it should be, because they're cutting this at that 3-day stage, it should have stopped here, but the FGF supported the growth of that limb bud all the way out here, and it differentiated properly. So that shows you that the apical ridge is important for the extension, and it's important because it's releasing FGF. Okay, so here's another thing that is important for that extension of the bud. So these cells are dividing. Why should they go out? Why don't they go this way or that way or the other way? Well, they're all these cells are polarized. So if you look at here, before there's a limb bud, you've got your somites here, and then you've got lateral mesoderm here. These lateral mesoderm cells are all polarized in this anterior to posterior direction, and they're actually facing posterior and moving posteriorly. And you can tell they're facing posteriorly because of where the Golgi apparatus is. It's always in the front of the cell in the direction it's moving. So all these cells are lined up this way. So as that limb bud starts to form, these cells now become kind of split into 2 or 3 sections here. And some of them are still kind of polarized in this direction and still moving posteriorly, but some of them flipped sideways, and now they're polarized in this direction. And that polarization is important because when the cell divides, it's always going to divide on this axis. So if you can imagine this as a single cell, if it divided, you would end up with 2 arrows, both pointing in this direction. Okay, so now you've got this. So when this arrow divides into 2, now you've got 2 pointing in this direction. So as they divide, they go in the direction that they're pointed. So here we are a little bit later with the emerging limb bud. You've still got cells going down posteriorly, but now you've got some that turn perpendicularly, and they're starting to go out this way. And now you've got your apical ridge. You start to support this growth with FGF, and they all polarize in this direction. So the ones in the core, the mesenchyme in the middle, are polarized in the outward direction, so they're forcing that limb bud out. But you also have cells that are going kind of perpendicular to those, or somewhat perpendicular, that's widening that limb bud. And the width is only like, well, the width of the limb from here to here will stay constant as the limb bud goes out. So the growth of the limb bud is only in length, not in width. But this kind of orientation here is forcing that out to where it's going to be the same width as what was before. Okay.
So why does it do this? Is it like a specific drug or a specific hormone or something that causes it to grow like this? Or?
Yeah, we'll get more into that in the next class, but basically it's this that's causing it to grow in that direction. So your Hox genes that were expressed here in the lateral mesoderm and the somites are causing the release of FGF, which is then giving you this self-generating thing, and that's causing the multiplication that's making them come out. And this is just basically a different way of looking at it, because at this point you've got FGF being released here and here, and now these cells are dividing and they're going to go in that direction. So what I don't get from the book is, why did they flip in this perpendicular orientation in the first place? I'm not really sure about that, but the outgrowth of the limb bud is because of that FGF system. Okay. Time is at 1:41. Okay. All right, well, I guess that's all I have for today. Why don't we do this as long as we're here? Let's look at this quiz and look at the answers to it. Any questions about today's lecture before we go on? Okay, I hope to finish limb bud on Friday, or limb formation on Friday. And I'd like to do a little Evo Devo if possible next week. And oh, I sent you an email. Hopefully you people all have gotten it. The vote went pretty solidly towards having the exam next Friday. So that's when we're going to have the fourth exam. It's not really a final, it's the fourth exam. Um, and if you've got some kind of problem with that, you shouldn't be any overlap or whatever because it's right in class time. But if you have any problem taking it a couple days or a few days early, let me know. We'll work that out. But be that as it may, be this as it may. This is what I'm doing. Yes, this is what I'm doing. Okay. This was pretty easy quiz, I believe. Hope you agree. Transcription factor that determines skeletal muscle. Ooh, skeletal muscle. This one. Let's find out. Transcription factor that causes muscle differentiation. Well, that would be MyoG. Transcription factor determines mesoderm. We've been talking about this all semester. TX factor that determines myotome. HAX3. Okay, and I think what I was trying to get across here is kind of the sequence of transcription factor activations that makes it go from ectoderm to mesoderm to muscle to differentiating into a complete muscle. Now this one, I believe we did this last week, but what the hell? A cell can either be actively proliferating or stop dividing and go into terminal differentiation. In muscle cells, this is because of interaction of MyoD and the cyclin CDK complex. Cyclin CDK is responsible for phosphorylating RB to allow release of E2F. We did this on Friday. Yeah. Cyclin CDK also phosphorylates MyoD, which causes it to be ubiquitinated and degraded. This keeps MyoD concentration low. When growth factors are removed, cyclin is no longer made, and CDK becomes inactive. This causes MyoD concentration to increase, and it upregulates Mr. Myog. It also upregulates P21, which is a CDK inhibitor and blocks CDK. Okay, so I think that was a new question. And that's what I have for you today. Any questions or comments? If not, see you back here again on Friday. Is anyone burned out besides me? Anyone want to just quit? Just stop. I don't know. Maybe it's just me. Okay, guys. Later.
I'm still checking, but I can't really find it.